Please welcome Colin and Justin to the S4 main stage.
Hi, good morning. Morning. So what Justin and I will talk to you about this morning is this IT-OT convergence future. We'll give you a perspective from GE on how we're looking at it. So when we think IT-OT convergence, we think about two things. We think about growth and moat. Growth in the sense that we're attacking these large opportunity spaces to drive revenue and profit growth, and moat in the sense that we're defending against the threats to our products, customers, and our reputation. So we'll spend the time walking through this with you. So what I'll do here is I'll start with first talking a bit about the needs and the dynamics in these spaces that drives us to think this way. So when we talk about needs, the industrial needs at this point in time, we think about four things. These are the four here. We first start with safety. How do I reduce the number of accidents, reduce the number of fatalities, reduce the liabilities? Then I think about productivity. How do I take down costs, reduce cycle time? Growth, market share, wallet share, adjacent space share. And then finally, how do I adapt to the dynamics that I see in the industry? And I do all of this simultaneously. I've got to first make sure I'm safe, improve safety, while driving productivity, increasing growth, all while dealing with a specific set of dynamics that are occurring in our industries. I have 5 of them here that are the major ones we look at. First, this notion of customers. So we're with GE, so we think about customers, but now we soon realize we've also got to think about end customers. I do jet engines, and I think about selling to airlines. However, we've realized that I've got to look at the customers of the airlines because I've got to follow the revenue all the way down to revenue origination. Let me give you one quick example. I have an airplane up there. This is the Boeing 777. So Boeing 777, the notion was, how do we get more revenue? Well, you get more revenue by having more people fly. What did the airline industry think? Well, we do that by using hubs. We go from an endpoint, a spoke, to a hub. We package all of the people in a hub, which is most efficient. We move them to another hub or to a destination spoke. That's efficient. If it's efficient, we reduce costs. We reduce costs, the ticket costs less, more people fly. That was the thought. Until we actually went out and spoke to end customers. Here's what Boeing and GE found out. We asked them, why would you fly? And they said 3 reasons. We've been on the internet long enough. We've seen far places. We want to do international flights. We want them cheap, but we hate hubs. Why do we hate hubs? 2 reasons. Every time we get to a hub, a plane is late, we get delayed. But more importantly, for new people, hubs are confusing. I get to a hub, a different language, I've got to find my way to a different terminal, don't like it. So what did Boeing and GE do? They created a 777. A smaller airline, not 600 passengers, 200 to 300 passengers, and they asked GE to build a bigger engine that could take you longer distances on less fuel. It opened 177 new routes from Chengdu, the 4th largest city in China, all the way to LA. From Barcelona to Naples, Florida. From London to New Orleans. New routes. As a result, in the last 10 years, 6% growth in travelers every year. You see the dynamics happening, right? Can't just look at the customers, but at the end customers. Let's look at the industries and see the dynamics there. We all talk about Amazon. So Amazon is well known to all of us, right? We think about retail commerce, we think about media, we think about web services. But Amazon is also in the industrial space. September 2000, Jeff Bezos talked about his long-time passion to be in space, started a company called Blue Origin. He spent $250 million of his own money until 2014 funding this. Then from 2014, he cashes out $1 billion a year of Amazon stock. What happens last year? He builds the first new generation rocket engine that actually is reusable and wins the most prestigious contract, the Boeing Lockheed contract. 20 years ago, none of us believed, even 10 years ago, that that Amazon could enter the industrial space. These industries are blurring. Governments in these industries are suddenly doing things like tariffs. Ford, $1 billion worth of cost incurred because of tariffs on steel and aluminum, a dynamic that's powerful. The dynamics associated with digital, we know well. Right now, when you look at IDC, 33 zettabytes data being produced this year on the planet. By 2025, 175. 5x growth in 7 years. It's coming from the cloud, the edge, but also the IT devices, 80 to 200 million IT devices. The proliferation of AI, not just the techniques, but the new tool sets that democratize AI. The significant drop in the price of components. 10 years ago, $600,000 worth of processing, computer processing, now costs $1,000. 60x drop. Bandwidth is 40x drop. Storage is 17x drop. The dynamics of the financials. Productivity has been a problem in the industrial spaces. We've got to deal with that. 1990 to 2010, 4% productivity growth. 2010 to 2015, 1%. After 2015, below 1%. While the IoT spaces grow. Another dynamic. When you look at IDC, we look at McKinsey, the ranges they give you is from $520 billion to $1.2 trillion by 2022. Lots of dynamics in the industry. And the most important one, the one we come to talk about here, is all about this notion of the growing security need. But even more important, the sophistication of the actors who are now playing in this space. Against that backdrop, we stepped back a G and we said, what do we do? How can we learn from the last 20 years that this has occurred in the consumer space, and what can we take there to learn new lessons? And that's the journey of growth we went on. Up here you see 3 examples. 5 years ago we looked at a number of examples. We found 3 that were very great in the sense that they showed leadership in the marketplace, which is what we're interested in, financial, mind share, and market share, but also they all use the same technique of digital transformation. Those are the 3 you have up there. If you look at the revenue numbers, you see some interesting things. You see the notion that Apple, 229 billion, Google 109 billion, Amazon 174 billion. Look at the number of years it took them. It took GE 106 years to get to $100 billion. Look at the rate of growth of these companies. All using the same technique. I have an Amazon example up there. Let me describe it to you. Here's how it goes. Amazon starts off thinking about demographics, groups of people, and the notion is simple. If I can get a demographic understanding, and I can say you belong to this demographic, and this demographic likes this book, I can sell you that book. They quickly went from demographic views to an individual view, from a view of a group to an individual. They look at what you bought, when you bought it, what you bought together, what you bought and sent, Mother's Day, Father's Day, Christmas time, what ads you looked at, what reviews you looked at. And they created a model of an individual. How you sell and when. How you buy and when you buy. That's a psychographic model. It's a model of an individual. How they buy, when they buy. A model of one. They have 300 million of those individuals. Then they use analytics. And what they did with the analytics is they said, okay, let me actually, rather than do simple segmentation, let's do profiling. If I'm a woman and I'm looking at baby outfits and looking at those ads, looking at those reviews, maybe I offer you a baby outfit at a discount. Profiling. If you buy the baby outfit, maybe what I do next is I offer you baby bottles at a discount. Prediction. If you buy that, maybe I go offer you a camera because you want to take pictures of your baby. They go from a model of one to a P&L of one. They know what you would like to buy, and they offer you the ads. Not any ads, specific ads. Model of one, a P&L of one. Then they put it in a platform to allow them to quickly repeat it and try things. And they take that platform and they go from books to retail, to media, to web services. Then they put the platform on steroids. They give you individual things like Kindles that you use to get more data about you. They put Alexa in your home so they listen to what you say and what you ask for. And the model of one gets stronger, the P&L of one gets stronger, the platform gets stronger. And that's the same thing that Google and Apple have all done. Well, we took that as a best practice at GE and we adapted it. We evolved it. We did the very same thing. We take our jet engines and rather than think about them as a fleet, can I look at the individual asset? Can I take all the information I have from the design, manufacturing, and service, and can I create a model of one? Then rather than use fleet analytics, can I use individual asset analytics? So what we did in fleet analytics is we made assumptions. We say we assume the asset will be used in this environment in this way, and if it did, then this part would fail in 3 years. But now if I have the individual information, I know exactly how it's being used in exactly this environment. I can say this part will fail in 6 years, so I don't need to pull the asset for service before that time. I get much greater availability. Same thing in performance. I said the asset is going to be used on average in this way in this environment, and so to minimize damage, I want to have a performance envelope and we'll cap it at this performance. But if I know exactly how it's being used, exactly the environment it's in, I can say we can go above this performance envelope for that specific asset. So I change your efficiency and your performance, which means I change your economics. So model of one to P&L of one. I put it in a software platform, and I take it from aviation to locomotives to healthcare to turbines. And this is what we created, and we called a digital twin, a model of that object that allowed us to do some very interesting things. So we take that physical object, we understand about the design, the manufacturing, the servicing of it, and then we take the streams of data that come from the sensors in the object. The temperature, the pressure, the infrared sensors, the moving coil sensors, the proximity sensors. We combine that domain knowledge with that data using machine learning techniques, and we literally create something that's called a digital twin. It's a personalized replica of this asset, personalized to the asset itself and the way it's used. It's living in the sense that all of the data that comes in constantly updates the model and it's learning. It's learning from its environment. It's learning from its actions. And we use this to drive actions. Because how you actually translate this into value is you've got to take an action from the insights you get. The actions are, we can tell a repair person to go repair it at this time, at the right time. We can tell a robot, go inspect this part of it at the right time to get more data. Or we can send a command to the control system that says, perform this operation to increase your performance, increase the electricity you deliver, increase the trust that you deliver to an engine. This is the digital twin. The power of the digital twin is the fact that as I meld it with the asset by constantly getting a stream of information from it, I constantly update that model. I constantly update the design, the manufacturing, the services, operational data, taking the data also off of sensors, and I can generate insights. I can now look at the remaining life on a part. I can now look at the efficiency of the operations, look at the utilization, and then drive an action, because with an action is how you actually get business value. And from that action, I get feedback. That feedback allows me to adjust these models, to adjust them at the right time, to learn from the model. Once I do that enough times, I got other insights that could allow me to change the design. This is the digital twin, a living, learning model. We've been doing this for the last 5 years, and we have 1.2 million twins up to 2017. We've had a lot more. We haven't counted 2018 as yet. $580 million worth of value being delivered. How is the value delivered? We do three things for customers. First thing is we give them early warning. You'd hate for that jet engine or that wind farm to break down right there with an hour's notice, a day's notice. Can I use this domain knowledge and this machine learning on the data that we have to predict 30 days in advance? Because with 30 days or even 15 days in advance, I can take an action. And I can take an action to actually remediate this problem to keep this asset working. That's early warning. With wind farms, I can predict when the generators, the nacelles, the bearings are going. If I can do that, I save $4,000 a year per turbine, per year on a wind farm. Huge amount of money when you consider the number of turbines you have. Beyond early warning, I can do continuous prediction. So I show you a jet engine here. What happens is that these jet engines fly in hot and harsh environments, environments where the contaminants are high with sun or other pollution, inside places like the Middle East or China. When you fly these jet engines into this environment, the contaminants get on the blades themselves and damage the blades. Once they damage the blades, they expose the metal. Once you expose the metal, you have a problem. So you need to bring them in. So what we've been doing is bringing them in every 400 or 500 flights. But then I create a digital twin that looks at all these design considerations, then understands fully the environment it's flying in and the way it operates, and it can predict. So rather than bring it in every 400 cycles, when it may or may not be a problem, it says for this airline with this engine, bring this engine in every 600 cycles. Bring that engine in every 800 cycles. I don't waste money with unnecessary service overhauls. Tens of millions of dollars saved. Then I can do dynamic optimization. I can look at a power plant and I can say, based upon that digital twin, I know exactly how I should run that plant. So in times when the electricity prices are low, what I may do then is I may say, don't use a lot of heat in the turbine, because when you raise the temperature in the turbine, you can generate more electricity, but you damage the life of the parts. Let's conserve the life of the parts. It may be a little bit inefficient. And when there's a very cold day, like during the winter storms we have, and the need for electricity to heat homes rises, the price of electricity is doubled. Now I'll let you fire it even hotter than ever before. Because I've saved that life of that part, I could overfire it and make the most profit. So I can make profit by early warning, by continuous prediction, dynamic optimization. That's how we get $580 million. What we've also done as part of this growth is we continue to enhance the twin. We now, because it can deliver $500 million of value, let's make sure we have limited business risk. Let's make sure we look at the data. If I build a model with these assumptions on the data, when I'm running the model, the assumptions must be same. If I took the data during summer, then that model really is a summer model. I want to make sure in winter I'm not running the wrong model. Then we have this notion of humble AI. This is where the AI knows when it should not be used. There's a region of competency that the AI system knows it should be used within. Based on the data I have, I work well in this region. When I go outside the region, I tell you. And I say, let's default to a robust model that was used many years before. So I don't hurt the system. And then I need you to help me learn more, get more data to make me more effective. So I go from humble AI to a learning system. And I can learn from my sensors, I can learn from the fleet, I can learn from simulations, I can learn from people. So I take all this capability, this is the growth discussion we've been having. How do I grow revenue? But that same power of that discussion allows me to build a moat. How do I defend against the threats that we have to our products, customers, and our reputation? This is what we'll talk about next, this powerful moat that we've built to protect the growth. With that, I'd like to have Justin come to the stage.
All right, thanks a lot, Colin. So, as we all know, ICS cyber threats are growing. That's why we're all here today. And they're growing at a rapid pace. But We're not just worried about rogue hackers, right? Over the last, call it few years, even decade, we've seen that the folks we got to worry the most about are nation states. Nation states are creating extremely sophisticated cyber attacks. Not only are they sophisticated in ways perhaps we haven't dreamt of, they're also very stealthy. Right? We've seen over the last few years, cyber attacks have been in industrial control systems for months, even years, going undetected. Now at GE, we've manufactured over 1/3 of the world's power. So we take protecting all that critical infrastructure very seriously. And at the research center, over the last few years, we've been asking ourselves, hey, what more can we do beyond what IT and OT is doing today to help protect all this critical infrastructure? So to answer that, I'm going to go back to a combined cycle power plant as an example. Now, I know a lot of you here are familiar with a combined cycle power plant, and you know they have hundreds of sensors, right? These hundreds of sensors, they're running 24/7. They allow you to operate your plant safely and reliably every single day. But what's also unique about these sensors is there's an underlying relationship, right? There's a thermodynamic relationship connecting a lot of these sensors together. Now, if I can understand those thermodynamics, I can figure out what the sensors should be reading and if they're right or if they're wrong. But in order to do that, I need some more information. I need to pipe all this sensor data in real time to my digital twins that Colin was talking about. Now, you can create a digital twin of a gas turbine like you see pictured here, or any of the other critical assets in a power plant, the steam turbine, the heat recovery steam generator. But what it's giving you is that deep understanding of the underlying physics that's happening in this asset, and that's critical. If I understand the physics, I can understand what the relationship should be between these sensors. And then I can again start to understand what's the story being told by these sensors. But I need one more piece of information. Now, as all of you know, the control system is critical, right? It actually dictates how the power plant should be operating. I need to understand what the controls is telling the asset to do. In a lot of ways, you could say the controls dictates the physics, right? Because if the controls is commanding a valve shut, there's no flow. So I have to understand what this dynamic is. I have to understand what the controls is commanding all the different parts of the asset to do. So what we did is we also created a digital twin of the control system so I can have this understanding. So now I have some powerful components. If I combine the digital twin of the physics with the digital twin of the controls, together with this real-time sensor information, I have a platform that can tell me whether things are operating normally or abnormally, and whether that's caused by a cyber attack. We call that platform Digital Ghost. Now, Digital Ghost is what we refer to as a real-time active defense. And it's more than, what you can think about, it's more than traditional anomaly detection, right? We've designed Digital Ghost from the ground up to detect stealthy cyber attacks, right? Even when sensors are lying to you, even when sensors are being spoofed, and I use the word sensors, but it could be controls nodes or actuators or other things. How do I tell what's really going on? So let me give you an overview of how Digital Ghost works. There's three main components to Digital Ghost: detection, localization, and neutralization. So for detection, I want to figure out is something anomalous happening, right? And how do I do that? And I go back to, hey, I combine this twin of the physics with the twin of the controls with this real-time sensor information. And now I got all the data I need, but how do I analyze that? So, the traditional way to do this, let's say you're looking at 20 sensors, we'd be able to look at it in the time domain, right? I plot all 20 sensors on an x-axis. The x-axis is time. The y-axis is the sensor values. I can try to figure out what's going on. That's what I've done most of my career, right? But the problem is it gets really difficult to figure out the truth, especially when sensors are being intentionally spoofed. So what we've done is we've made some unique advancements in AI and machine learning. And what we're trying to do is say, hey, can I pull out correlations between the sensors, right? There's statistical correlations, domain-specific correlations. There's hundreds of correlations amongst these sensors that I can pull out to tell me the truth about what's going on. Not only are there correlations between sensors, but I can actually pull out sensor-specific intuitions. So now, instead of looking at these 20 sensors in 2 dimensions, I can look at them in over 100 dimensions. And that gives me this tremendous ability and accuracy to determine the difference between normal operation, a traditional fault, and a cyber attack. And that's detection at a global level, right? Hey, something's wrong, something's not operating right. The next step is to locate exactly where the problem is, pinpoint the issue. Now, this is very, very difficult in a control system because it's closed loop. So if you think about it for a minute, if I'm a gas turbine and I'm a hacker and I put more fuel intentionally into my gas turbine, everything gets hotter, right? It's a huge cascading effect. All the sensors start to move as a result. So if you're trying to pick out who's independently being attacked versus who's just reacting to the increase in temperature, it becomes very difficult. It's a chicken and the egg problem. This is something we got to solve and solve accurately. So how do we do that? Well, we combine deep domain knowledge with the twin of the controls and some advancements in estimation to determine the causality, right? And if I can know that, I can tell you precisely which sensors are compromised. Now, detection and localization, those are both passive, right? They detect and locate within a matter of seconds and tell you that something's wrong. The next step, neutralization, is what we consider our active defense. And what are we doing in neutralization? What do I even mean by neutralization? What I don't mean is to delete the virus, right? What I mean is to remove the effect of the virus on the operation. Let our operators continue to run their assets normally. So what's happening? Right now, you have compromised sensors, you have compromised actuators. I know specifically what they are. So what I need to do is I need to create an estimate of what those sensors are, right? So, one option could be, which was traditional, is a virtual model, a virtual sensor. Now, a virtual sensor, it has predetermined inputs. It goes into a transfer function, a model, spits out an estimate of a sensor. The problem with that, as we thought about it for cybersecurity, is you have no idea what inputs or what sensors you're going to be able to trust until the cyber attack has occurred. So the challenge, and neutralization is by far the most difficult part of Digital Ghost. The challenge was to dynamically, on the fly in real time, based on whatever sensors are left that I trust, create models of these sensors that have been compromised. And these models have to be accurate for transient operation, and they have to be accurate enough to safely and reliably continue to operate the plant. So it's a massive challenge. But if I can do that right, I can have active defense. I can let our operators continue to run their assets, right, which is critical. You want to keep the power grid running. You want to keep your weapon systems going. You want to keep your critical infrastructure running. You don't want to have to shut down when the cyber attack tells you to. Now, detect, locate, neutralize, all this happens in a matter of seconds. So we're really changing the time frame in which it takes to respond to a cyber attack. Now, we view Digital Ghost as an additional layer of defense in this defense in depth strategy, right? So we view it as complementary to all the advancements that are being made in the IT and OT domains. So this is kind of a high-level overview. I'm going to walk through a hypothetical example of how Digital Ghost would work, and I'm going to continue to pick on the power plant, especially our gas turbine here. So if I'm an attacker and I want to manipulate this gas turbine, let's just say I decide to attack 6 of the sensors on the gas turbine, right? And these 6 sensors, what I'm going to do is I'm going to use these 6 sensors to change the way the asset is operating. And I'm going to cause the gas turbine to start overfiring, right? Increasing the firing temperature and heating up. But I'm going to do it in a really smart way so that I'm spoofing the sensors. And the controls has no idea, right? The controls sees normal data. It thinks everything is operating properly. Therefore, the operator has no idea that there's an attack occurring. They're looking at their trends. They have 0 alarms. They think life is good. The reality is there's an attack underway, and Digital Ghost is able to detect it. But why can Digital Ghost detect it? So what it's doing is it's looking at the full story that's being told by all the sensors, not just these 6. If you think about what's happening from a physical perspective, hey, I'm injecting more fuel into this gas turbine. That's going to make things hotter. That means hotter air is going out my exhaust. So that means going into my heat recovery steam generator, heat recovery steam generator, I'm going to have hotter air, which is going to produce different steam at different pressures, temperatures, and flows. The controls are going to react differently. That's going to cascade into my steam turbine and then my generator. See, there's hundreds of other sensors that saw this attack taking place. And what Digital Ghost is doing is it's going to look at all the correlations that our AI is enabling to say, hey, there's no way the exhaust temperature can be 1100 degrees. It has to be 1200 based on the physics, right? Somebody's lying to you, there's an attack occurring. So what we've done here is we've tested our Digital Ghost detection algorithm pretty vigorously over the last few years. We've leveraged the controls development platform from our power industry, which is used to actually develop the controls that run on these power plants. And that platform has a very, very high fidelity transient model that's connected to the real controls that would run in a power plant. So I can do some unique things, right? I can replicate exactly how a power plant normally operates. And what we've done is we simulated over 600 normal cases. What does that number mean? That number means essentially, call it 20 years of operation, right? The entire ambient range that plants around the world would see, the degradation curves that you would expect over time, the different grid events that you can see across the world, as well as transient operation. We threw it all in there. And the goal is to say, hey, what's our false positive rate? Right? How often are we saying that something's wrong when really it's just a once a year transient event? The second thing we did is, well, how good are we actually detecting a cyber attack? So we simulated over 900 different cases here. And the interesting thing here is because we have the real controls, we can actually delve inside the controls and manipulate nodes, manipulate sensors, and do a lot of different things. So what does this 900 mean? It means, hey, we're attacking individual sensors. We're attacking different nodes. We're doing staged attacks where we're attacking multiple sensors over time. We're crafting stealthy viruses that the controls won't detect, that won't generate an alarm, but will manipulate operations. So we put that in these 900. What we're able to achieve over the last few years is an accuracy of 99%, right? And that's a 1% false positive rate and a 1.2% false negative rate. And how do we get there, right? It's this combination of the deep physics from the twin of the controls, with these advancements in AI and machine learning that can get this type of accuracy. So that's in simulation, and what we did is we took it to the field. We said, let's go see how this actually operates. So we went to 10 different gas turbines and gathered data from 10 different gas turbines all across the world. And this represented about 500 days of operation and about 12,000 hours of data, and this is 1 second data. And we did not, go out in the field and inject cyber attacks. We don't think our customers would appreciate that. So what we did is we're asking the question is, hey, all this data is normal operation. We see the extreme ambient changes. We see the really different ways our customers operate these things and the way the grid perturbs them. And what's our false positive rate? Okay, because this is all normal operation. What we're able to achieve is a false positive rate of less than 1%. So these are fantastic results. It gives us this confidence that I can accurately say, hey, is this in a normal operation or this is an attack? And that enables me to go to the next step, which is localization. Now again, with localization, the goal here is, I said, at a high level, something's wrong. Now I want to pinpoint what sensor is the problem. Now I'm a controls engineer. I've operated multiple power plants. I know that when something goes wrong, even if you have the trip log and the event log, it's still a pain to figure out where the precise problem is. It can take hours. If you don't have the right expert, it can take days, right? So one of the personal passions of mine was, hey, I want to make this instant, right? I want to tell the operator where the problem is so they're not wasting time finding the problem. And that's what localization does. And we put localization through the exact same testing on the simulation as the detection algorithm. All the same test cases. We then ask the next question, okay, great, you found something was wrong. Can you pinpoint what sensors it was? And we got similar results, around 99% accuracy. And that's important, right? We have to be very, very accurate because what we want to do is neutralize, right? And we can't neutralize a real problem. We're trying to neutralize what we think is a cyber attack, right? We don't want to mask a real issue. So we have to be able to very accurately figure this out. And now that we can do that, we go to the next step, which is to restore normal operation, right? This is giving our operators the chance to continue running if that's what they want to do. And how does this work? Well, look, there's 6 compromised sensors here. So I need to reconstruct those 6 sensors, right? Because those 6 sensors are causing my bad operation. So I need the twin inside my digital ghost to use all the remaining sensors and come up dynamically with a model of what those 6 should be. And once I could do that accurately, what I need to do is reroute the controls, right? Instead of the controls listening to those 6 compromised sensors, I want it to listen to the estimates coming from Digital Ghost. Now, this is really difficult, right? Because remember, we need to enable transient operations. So we need to be able to replicate these sensors across the whole transient, path, and do it safely and reliably. And it's been a really big challenge for the team. But if we can do that, we can enable our operators, to keep their plants operating. So the goal here is, let me show you, what I wanted to do next is show you some recent results we have from neutralization. What we've done, and again, we continue to pick on the gas turbine, is we actually attacked the gas turbine, and we were monitoring 15 sensors. So what you see up here on the chart are 6 sensors that we're going to attack out of those 15. Now, in the upper right-hand corner is what we call the reference signal, the truth. That's megawatts. That's to show you what the simulation is doing. What the simulation is doing is going to go from 40 megawatts. We're going to load the turbine up, back down again, and through another transient. So we're going to do transient operation. And at the 200-second mark, what we're going to do is we're going to attack all 6 sensors simultaneously. So what does Digital Ghost have to do? A, it has to detect something occurred. B, it has to locate that it's these exact 6 sensors. And then on the fly, it's got to reconstruct all 6 of these sensors from the remaining 9 that haven't been attacked. And again, we could have looked at more sensors, but we just looked at 15 for this. So what you're going to see is 2 signals on each chart. Red is going to be the truth signal. That's what the value should be if there was no attack occurring. What really happens is after 200 seconds, all these sensors are useless, right? We don't use them for Digital Ghost at all, and they're disrupting the control system in a negative way. Then you're going to see the blue sign, right? The blue signal is our reconstruction, and the goal is that these should match as close as possible. So I'm going to go ahead and play these results for you. So what you can see is that, there's not too much difference between the red and the blue, right? That's our goal. We were able to achieve an average error of around 1%, with the min and max peak errors a couple of percent more. And this is something we've never been able to do before, right? What you're seeing is a real-time reconstruction of 6 sensors just using the data for the remaining 9. Now, this doesn't mean we can go and, reconstruct everything, right? But this is an important, critical step forward to building this new type of resiliency. And to say we can do it, right, for transient events, for transient operation, and give our customers the confidence that they can continue to safely and reliably operate their assets. So over the last few years, we've been working with the Department of Energy on building out this Digital Ghost technology for thermal power. We'll be moving forward in 2019 and expanding that relationship with the DOE and taking Digital Ghost to renewables, taking it to the oil and gas sector, as well as transmission and distribution. And what we're going to do is continue to build out this radical idea of neutralization, which is phenomenally hard to do. And that's what they're really excited about, because what their end goal is, hey, they want to keep the power grid running. Right, the other parts of the government, they want to keep their weapon system going, despite the fact that there's a cyber attack in place. They don't want to shut down. The other thing that we've realized over the last few years is that this technology is a horizontal technology. It doesn't apply to just these areas that you see here. It's broadly applicable to any type of critical infrastructure with an industrial control system. Also in 2019, we're going to be taking our detection and localization technologies to our customers. Later this year, we're going to be helping them protect their critical infrastructure with both of those aspects. Just to wrap up here, We're really excited to be pushing this technology forward. It's really fun to really work to make the hacker's job a lot harder. And we're definitely looking forward to continuing working with all of you on improving the security of our industrial control systems. Thank you.